Hey guys, a number of you have expressed some interest in the first-person controller from this little piggy, which could sort of navigate a spherical world. So yeah, that's what we're going to be looking at today. First of all, if you wish, there is a little package in the description, which you can import into Unity. It's basically just the model that Daniel created for this little piggy, and you could just as well use Unity's default sphere or something. But yeah, this is far more pleasing to look at. Here we go. So the first thing we're going to do before we actually work on the player controller is just to set up a system whereby objects in the scene will be sort of pulled towards the center of the planet. So let's just create a folder for our scripts to keep things nice and tidy. And I'm going to create two C# scripts, one called something like gravity attractor, and this script will be applied to the planet, and it will basically be responsible for pulling all the gravity objects in. So that's the other script that we're going to create. Let's call it gravity body. This will be applied to every object that we want to be influenced by the gravity attractor. So let's go ahead and apply the gravity attractor script to the planet object. And I'm going to open this up in MonoDevelop. And let's first of all create a public float gravity, just so that we can easily set how powerful the gravity is. And I'm going to set this by default to something like -10, just somewhere around there. And now let's create a public void. We can call this attract. And this method is going to be called by each gravity body in the scene. And each gravity body will pass in its own transform. So we'll create a parameter for that, transform body. And what we want to do first of all is to orient the body so that its up axis is looking at the center of the planet. And then we want to apply some downwards force to the body's rigid body. So the easiest way for us to orient the body correctly is using a method called quaternion.from_to_rotation, which basically takes in two directions, the body's current direction and the direction that we want it to face. So let's first set the direction that we want it to face. Vector3, we can call it target direction, and that's the target direction is basically the direction between the body and the center of the planet. That's the direction that we want it to face. So we can get a direction between two objects just by subtracting their positions. So open brackets, body.position minus transform.position. Oops, that's transform with a small t. Transform.position. Transform being just the transform that the script is attached to, which should be your planet. And now we just want to normalize this. There we go, so that it's always the same length because it's just a direction. And now the current direction is the body's up direction. So we can set that, let's just say vector3 body up is equal to body.up. Alright, now we can set the body's rotation. Body.rotation equals to quaternion dot, and we'll use this method I was talking about, from_to_rotation, pass in the current direction of the body's up direction, and the target direction, which we've already set. And now, so this method is supplying the rotation that needs to occur to go from body up to target direction. And we want to add this to the body's current rotation. And the way we do that with the quaternion is just by multiplying the current rotation. So we just multiply this quaternion by the body's current rotation. Now, all that's left to do in this class is to apply some downwards force to the object to simulate the gravity. So we can just say body dot rigid body dot add force. The direction we want the force to be in is the target direction, and we can just multiply this direction by our gravity. Alright, now let's go back into Unity and open up the gravity body script. The gravity body must always have a rigid body attached to it. So let's just say here, require component type of rigid body. This means that whenever we add this script to an object, a rigid body will automatically be added along with it, and we won't be able to remove the rigid body ever because it's required by the script. Alright, so in the awake method, which is just like start, let us say we need to get a reference to the gravity attractor script. So let's create a field for that, gravity attractor. We can just call it the planet. And we're going to give the planet a tag. We'll probably just call it planet, so that we can find it from within this gravity body script. We can say planet equals GameObject dot find GameObject with tag planet dot get component, and the type of component is gravity attractor. There we go. So now we've got a reference to our planet. We also want to set two things about our object's rigid body. Since in the gravity attractor script, the body's rotation and gravity is all being calculated here. So we want to first say rigid body dot use gravity equals false. We've got our own custom gravity, and rigid body dot constraints is equal to rigid body constraints dot freeze rotation. So we don't want the rigid body to do its own rotation because we're rotating it manually here, and we don't want it to do its own gravity because we're simulating gravity here as well. Alright, now let's create another method, void fixed update. Fixed update is like the update method, except it gets called multiple times per frame to always be called at a constant rate, and it's basically the method that you should do all your rigid body physics calculations in. So in here, all we're going to say is planet.attract, and we're going to pass in our own transform. Alright, let's test this out. We can create maybe a capsule is a good shape for our player. And let's just move this so that it's positioned above the surface of our planet. You can add the gravity body, and you can see we've got a rigid body added automatically. Just to point out, one can of course disable use gravity here and freeze the rotation here. That's all that we're doing from script. It's just that we might as well do it automatically rather than have to worry about it every time. Alright, let us not run it yet. First, we need to remember to add the planet tag. I've already got it set up here, but basically just, I'm sure you guys know this, go to tag, create a tag called planet, and of course remember to actually apply it to your planet with the gravity attractor script attached. So let's run now and see if everything works. It seems to be working. This dropped down nicely. Let's put it somewhere else, maybe over here, see if it still works. Yep, that's working nicely. We can fling it around a bit. Oops, what have I done? I think I flung it a bit hard. But yeah, you can see it's working nicely. Okay, I'm having to backtrack a little bit because my mic started emitting strange staticky noises. But anyway, what we're going to do now is create the actual first-person controller part of this. So first of all, let's make the main camera a child of our capsule. Let's actually name the capsule player. And set its position just to sort of roughly head height, and make sure its rotation is all zeroed out as well. So if you've never really made or worked with a first-person controller before, basically how it works is our whole player capsule is going to be rotating like this with the mouse X input, and the main camera will rotate on its X-axis for the vertical or Y mouse input. Okay, so let's create a C# script. We can call it something like first person controller, and let's attach that to our player and open it up. All right. Okay, I don't know why I deleted those methods. I actually want them. Just quickly rewrite them. All right, so the first thing that I want to create is just two public floats for our mouse sensitivity. So we'll have a mouse sensitivity X, and I'll set that to maybe 250 by default, and also a mouse sensitivity Y. And now, since we're going to be rotating the camera, we also need a reference to the camera, so we can just say transform, let's call it camera T for transform. And in the start method, we can just set the reference to that camera, just camera T is equal to camera.main.transform. So camera.main just finds whichever camera in the scene has got the main camera tag applied to it. Alright, so now in the update method, we can rotate our little capsule around, transform.rotate vector3.up multiplied by our input, our X mouse input, which is set up in the input section of Unity by default. So we can just say input.getAxis mouse X, and we multiply this by time.delta time. Alright, so that should be, oh, hold on, I also want to multiply by my mouse sensitivity. Alright, so now we should be able to rotate this guy around. We just can't look up or down yet. So with the up or down, we obviously want to have some constraints so that we can't sort of look around 360 degrees. I found that sort of -60 to 60 works quite well, but you can find your own values for clamping the look rotation as well. So since we want to clamp this value, we're going to just store it in a float. We can call it maybe vertical look rotation. And vertical look rotation we will increase, so plus equals the mouse, get axis, the vertical mouse movement each frame, mouse Y, multiplied also by time.delta time, and let's not forget our mouse sensitivity Y. Alright, now we want to clamp this, so we can just say vertical look rotation is equal to, and we can use the handy mathf.clamp function. We pass in the current value, vertical look rotation, our minimum value, which we can set as -60 and 60. Alright, and now we can just say camera T dot local Euler angles. Don't forget we want it to be rotating around its local x-axis, and we can say that's equal to vector3 dot left, which just specifies that we're working with the x-axis, and we'll multiply that by the vertical look rotation, and that's all. Let's see that that's working quickly. And it is. We can look around, we can look up, but we can't look that far up, and we can look down, but not that far down. Alright, perfect. So the next thing to do is allow our character to move around. Now, Since we're moving a rigid body here, we're going to be moving it with rigidbody.movePosition. Like I said before, we want to do our physicsy stuff in fixed update. But I actually want to receive my input in update, because there's no reason to sort of receive our input multiple times per frame. It's going to stay the same. So let's create a vector 3. We can call this move amount, and we'll calculate our move amount in the update method. We can say move amount is equal to actually, let's not do that. Let's create a vector 3 first called move direction, move dir for short, and this can be equal to a new vector 3, and we can get, first of all, our input.get axis raw horizontal. So this is just by default the A, D, or left and right key, and I'm using get axis raw. If you just say get axis, then it will do its own default smoothing. If you get axis raw, it will just return the raw values, so either -1, 0, or 1. And I'm getting the raw because I want to do my own smoothing rather than let Unity handle it. So for Y, that's 0, and for Z, input.getAxis raw once again, this time on the vertical axis. Alright, and let's normalize this once again so that it's always the same length. So for example, if we're holding down left and up at the same time, we're not moving further each frame than we normally would be able to. Now let's create a vector 3 for our target move amount, and we can set this to our move direction multiplied by our move speed. So let's create a public float for our move speed. Public float, let's call it walk speed. I'm not actually going to do running in this tutorial. I'm sure you can figure out how to do it. Basically, just create another float for run speed, check if the run key is down, and if it is, multiply by the run speed over here instead of the walk speed. Now we want to smooth our move amount vector that we created over here towards target move amount. And to do the smoothing, I am going to use vector3.smoothDamp. So we can say move amount is equal to vector3.smoothDamp, and this takes in the current vector, so we pass in move amount. It takes in the target vector, target move amount. It takes in a reference to a vector 3 for the current velocity. So we have to create a vector 3 for that. We can call this smooth, maybe smooth move velocity. So we're not going to actually modify this. What the ref key does is it allows the method to actually modify this value that we have over here. So it's using that to calculate how much to smooth each frame. And now, last of all, we've got the smooth time. So the lower this value is, the faster it's going to smooth. So we can set it to something like maybe 0.15. We don't want to set it too high because then our movement's going to feel really slippery. So you can just experiment with that value, see what feels good. And now in fixed update, all we need to say is rigidbody.movePosition, and we first need to get our current position, and we want to add to that the amount that we're going to move. So rigidbody.position plus move amount. Okay, now one thing we've got to be careful of is move position is working in world space. So we want our character to move. Oops, I didn't mean to open that. We want our character to move. If we say, for example, hold down the up key and we want to move forwards, we don't want our character just keep moving like this. As it rotates, we wanted to move forward on its own local axis rather than forward on its global axis. So we need to I can never find monodevelop. We need to change this vector from world space into local space. So how we do that is actually very simple. We say transform direction, and we pass in move amount, and that will change it from world space to local space. And now we multiply this by time dot fixed delta time, since we're in fixed update. And there we go. Let's see if we can walk around now. I am currently not at all able to walk around. Let's see what the problem is. We're getting our move direction, horizontal and vertical, we're normalizing it. We're setting, our walk speed is 0, alright. We can set that by default to 8 maybe. Since this is a public float, changing it in the script's not actually going to change anything. It's still 0 in the inspector. So I'll set that to 8 over here as well. And yep, now we can walk around. Okay, this is more like a very fast trot, so let's turn that down a bit, maybe 6. Okay, it's still going along at quite a speed. Maybe 4 is more sedate. Yeah, okay, that's a nice casual stroll. Well, it's actually still quite fast, but anyway, I'm happy with that. Now, the last thing that I want to cover in this tutorial is jumping. So that's not too difficult. The only problem is we need to know when we're actually touching the ground. We'll worry about that in a moment, though. Let's first get our input. So we can say if input.get button down jump, and once again jump is already set up in Unity by default. I think it's assigned to the space key. So when we press jump, we basically want to say rigid body dot add force, and the force that we want to add is in our own up direction, our local up, multiplied by, we'll create a field for jump force in just a moment. Let's go over here, public float jump force. Add force, you usually need to give it quite a high number if you're just setting it once rather than multiple times in fixed update. I should just say, to prevent any confusion, the reason we're adding force to the rigid body in update here, rather than, as I keep saying, do all your physics in fixed update, it's because we're just adding it once when you press the jump key. If we were adding it over multiple frames, we'd use fixed update. So jump force, let's set it to 220, and alright, so at the moment you'll just be able to keep pressing jump. Since we're not even checking if we're on the ground, we can just... Okay, and we should start coming down any moment now. There we go. Alright, so we need some way to check if we're actually touching the ground and only allow the player to jump if you are. So we're going to do this using a raycast. So let's create a bool over here, a bool grounded. So if grounded is true, you can say if grounded, then add force. Okay, and each frame we can just set, we can set grounded equal to false. So we'll just reset it each frame, and over here we'll do our check to see if we are in fact touching the ground. So we're going to need a ray. We can just call it ray equals a new ray, and ray takes in two vectors, an origin and a direction. So for the origin, we can just get our transform.position, and for our direction, transform dot, is there transform dot down? No, there isn't, so we'll use transform dot up, only negative transform dot up. Now we're probably also going to need a, oops, I didn't add a semicolon. We're also going to need a raycast hit. We can just call that hit. All right. Now let's do our actual raycasting. Actually, let's also create a public layer mask. And we can call this collision mask, because actually let's call this, rather, to be more precise, our grounded mask. So these are all the layers that if our raycast hits an object in this layer, then we're going to assume that we're standing on something, and thus we'll be able to jump off from it. Okay, so if physics.raycast, we pass in our array, and we say out hit. Let me just mention that ref and out do basically the same thing. As I explained earlier, ref is allowing the method smooth damp to actually modify this value that we have here. Usually when you pass a variable into a method and the method uses that variable, it creates its own sort of local copy of the variable and doesn't actually modify its value. But if you use the ref or the out keyword, then it will actually be changing that variable's value. So what's the difference between out and ref? I'm not super clued up about this actually, but I believe that out doesn't require the variable to be initialized. So if we're using ref here, we'd have to say this is equal to something. And just in case you're wondering, you might think, well, smooth move velocity, we haven't set it equal to anything here either. But if you set variables outside of a method, they are automatically initialized to 0. So this will be by default equal to vector3.0. Anyway, quick random lesson. I hope that's correct. All right, so out hit, and what else do we want? We want our layer mask. What did we call that? We called it our grounded mask. Grounded mask, and a distance. Okay, now I should just be a bit careful in explaining this. We are currently using a capsule for our player, so when we say transform.position, it's getting the center by default of the capsule. So if you're rather using a character model that you've created yourself or downloaded or whatever, the origin probably is going to be at the base of the character, and you'll have to have moved up the capsule collider along its center Y or something like that. If that is the case and your origin is at the base, then your ray obviously can be a lot shorter than if we're going from the center here. Since we're going from the center, our height of the capsule collider is 2, so the sort of distance from the center to the bottom is of course half of that. Half of 2 is 1, so we're going to do 1 plus a little bit just to make sure that we're always hitting the ground, even if we're standing on a slope or something like that. So if your origin is at the base, basically just use a tiny little distance, like maybe 0.1. But since we're using the capsule collider for our distance, we'll say 1. And to make it clear, we'll say 1 plus tiny little distance, something like 0.1. All right. So we can basically, inside of this, just say grounded equals true. So yeah, I guess actually we don't need this raycast hit. We don't need to check like tags or anything, but we might as well just leave this here, because if you continue work on this controller and want to do some more advanced stuff, like say playing audio when you're playing different audio when you're walking on different surfaces, you could use this to check the tag of the surface you're on to see whether you're walking on grass or rocks or whatever. So yeah, it's useful to have anyway, even if it's not entirely necessary at the moment. We're getting errors. Errors. What's wrong? Physics.raycast, ray, outhit, grounded mask, and distance. Have I got variables in the wrong order here, or what's wrong? Let me just see. Physics.raycast takes stuff in what order? It takes array. We can just toggle through these. This is the one that I want to use. Ray, Okay, so the distance comes before the grounded mask. Yes, yes, that's right. Oops. The distance becomes before the grounded mask. All right. And I must remember to delete that. Okay, let's see if everything's working now. No more errors. Of course, that doesn't mean everything's going to work, but let's give it a try. Okay, so we can walk around. You can see we've got some beautiful smoothing here, courtesy of Smooth Damp. And can we jump? We can't jump. Oh no. But that's because, can you guess why? Do you know why? It's because our layer mask, our grounded mask, is currently set to nothing. So let's create a layer for the ground mesh. Add layer. We can call this the ground. And let's apply it to the ground. We might as well just go ahead and apply. I don't want to create a layer specifically for tables, so we can just call this maybe something like collision and add the collision layer to that, and on our player set the grounded mask to both ground and collisions. And now let's see if it works. Alright, we can jump. We can't jump multiple times in the air. Let's jump around. Let me find that table. I want to jump on that table. I seem to be getting further and further away from it. Hold on. I think I'm heading in the right direction now, am I? Yes, there we go. It's up on the table. And we can still jump on the table. So, yeah, everything seems to be working nicely. And yeah, I mean, with a character controller, you obviously want to keep optimizing it and adding little improvements. But just for a nice base that works on a spherical world, I think that is sufficient. So yeah, let me know if there's anything else you want me to sort of if you want me to continue with any aspect of this tutorial. But for now, I think that'll do. And also feel free to leave any requests for other tutorials you'd like to see in the description. Not in the description, in the comments, please. Yeah, alright. Thank you very much for watching. Hope you've learned something, and cheers.